So, good afternoon, everyone. Welcome to the second session of our workshop on extended mass distribution of primordial black holes and primordial magnetogenesis. This is part of the Friends of Friends meeting, and it is the second session of the workshop, which will be precisely on magnetogenesis. This is the main topic for today. So today's session will be a collaboration between Marcelo Rubio of IFPU in CISA and myself, okay? And first I will start with a brief theoretical overview of how primordial black holes can actually be a mechanism for magnetogenesis. And then we will have a hands-on part, which will where we will deal with a programming exercise in order to use this formalism to do some interesting computations. So, okay, so look forward to that. Okay, so first I will recap a little bit of what was discussed in yesterday's session. So essentially, we're considering primordial black holes as a dark matter candidate, right? And basically, this is not a new idea. It has been, well, primordial black holes have been considered essentially since Hawking in the 70s, okay? But like Nelson Padilla explained yesterday, they're hard to obtain unless you have some sort of enhancement in the power spectrum of fluctuations that give rise to them, because black holes are extremely dense objects which are hardly occurring naturally unless there is a mechanism to actually enhance the density fluctuations, right? So the energy density fluctuations. So okay, but you can consider such mechanisms. And the point is that, 1 second, let me deactivate. 1 second. I thought, give me 1 second. I thought I had deactivated WhatsApp, but it seems that I didn't. Okay, now. Okay. Okay, right. Okay, so let me just go through this. Okay, so first we will review how primordial black holes can source the dark matter, and then we're going to talk about two different mechanisms through which primordial black holes can gain a magnetic field, right? They can generate a magnetic field, and from there we're going to use that in order to derive a cosmological primordial magnetic field generated by the black holes themselves. So the idea is the following: primordial black hole as a dark matter candidate, then two different processes through which primordial black holes can acquire a magnetic field, and then how those ingredients, namely a certain dark matter distribution, right, consisting of primordial black holes, and the fact that each of them is endowed with a magnetic field, generates a cosmic magnetic field in the large scales, which can serve as a seed for the present day magnetic field at cosmic scales. This is the overall idea. Okay. So, like you all know, dark matter comprises 23% of the energy budget. It is the dominant matter component, right? It's not the dominant energy component, but it is the dominant matter component, right? And there are several candidates, okay? And we are going to focus on the primordial black hole. So there's some very good reviews by Carr on constraints that you can place on black holes being the dark matter, but considering monochromatic mass functions, right? So yesterday, Joaquin explained a little bit, was that it was proposed in this paper, an algorithm to translate constraints for monochromatic primordial black hole distributions into constraints for extended primordial black hole distributions, right? So the point is that we have developed an algorithm, right, that provided a set of restrictions, of constraints, right, for monochromatic primordial black hole populations that can automatically be translated into a corresponding constraint for any given form of an extended mass function, right? So this is the idea. So you have some sets of constraints, right? Different constraints. Joaquin referred to them as low mass, intermediate mass, and high mass constraints. And given those constraints that you can, for instance, take from a table or from some reference material, you need to provide the algorithm with an extended mass distribution, and then you can obtain the corresponding constraint for the extended mass distribution. Okay, right. So here's a pictorial representation of that. So this extended mass distribution, which is shown as the red line, is a Schecter form, and is the one that was discussed in yesterday's session, right? A monochromatic one can be represented by like a very narrow, let's say, very narrow log normal in log mass space. So of course, a delta you cannot represent in a density graph, but you can make a spike arbitrarily close to a delta. Okay, so it's essentially some enhancement in power at a certain particular mass scale that gives rise to all black holes having the same mass, essentially, right? Okay, and in particular, like Joaquin discussed yesterday, in this paper, we show that there are certain regions where for primordial black hole mass distributions of the extended form, of the Schecter form, characterized by a power law exponent and by a characteristic cutoff mass scale, there are certain values of these two parameters, of the m star, which is the cutoff scale, and the exponent of the Schecter, where 100% of the dark matter could be made of primordial black holes. So these are the kind of regions that we're going to consider in this exercise that we're presenting here today. So namely, we're considering parameters for the extended mass distribution where all dark matter can be made from black holes. Okay, so it is consistent with the current observational constraints. Okay, for more details on this, I refer you to this paper, the Sureda et al. 2020. Okay, so now let's get to today's topic. Okay, so first I will present two different mechanisms from where the primordial black holes can acquire a magnetic field. Okay, so the first one is the Biermann battery process. Okay, which is a standard dynamo process, and essentially you require the density gradient of electrons and the pressure gradient to be misaligned, so that they're not parallel to each other. Okay, and that induces a dynamo current of charge, right, which of course generates a magnetic field. And you can find more details of the model in this paper, the Safarzadeh 2018. Okay, and the point is that this process is naturally occurring in accretion disks. Okay, and in particular, you can consider primordial black holes to also be subject to this process. Okay, so this is the first mechanism, just a standard dynamo process. The second mechanism that we're going to consider is more exotic. Okay, and it considers that at an early cosmic scale, for instance, during a cosmological phase transition, like for example the grand unified, the great unification phase transition, for instance, the universe can give rise to topological defects. So namely, topological defects can form as a result of a cosmological phase transition, similar to the nucleation sites in a supercooling of a liquid, for instance, right? And once these objects form, if they do form, which we don't know, they could be accreted by primordial black holes. Okay, so the exotic part here is making the magnetic monopoles, but once they're there, it follows naturally that primordial black holes should accrete them, because primordial black holes would turn to form around the densest peaks of density. And if the distribution of magnetic monopoles tracks the distribution of density, which they should just by probability, then the formation sites of the primordial black holes will be preferential regions where overdensity of magnetic monopoles will also reside. Okay, so this is the key point. Okay, and the interesting thing here is the following. The interesting thing here is the following, that these magnetic monopoles in principle can have like either north or south magnetic charge. This sounds weird, right? But you know, unlike electric charge, which is positive or negative, magnetic charge is either north or south, right? Like a magnetic dipole has a north pole and a south pole, and the magnetic flux goes from a north pole to a south pole. So the magnetic charge is either north or south, right? So essentially the magnetic monopoles can either be north monopoles or south monopoles. but because they would occur with equal probability, the net magnetic charge that a certain primordial black hole of mass m would acquire would scale as the square root of the mass. Essentially, it's like a Poisson process, right? It's like you have a one-dimensional random walk on charge space, so either north or south charge, and the root mean square of the net charge modulus, right? Without concern for the sign, would be the square root of the accreted objects, right? So just by imbalance, like naturally statistically occurring imbalance between north and south charge. Okay, so this is the key point. Now, what kind of magnetic field would be generated by this mechanism? Okay, so it is well known that in a standard dynamo, the dominant multipole of the magnetic field is a dipole, right? Simply because of the fact that you don't have net magnetic charge, well, unless you propose it, which we'll do in our monopole mechanism, but usually you don't have net magnetic charge, so therefore you don't have a magnetic monopole in a distribution of magnetic field, right? The divergence, like if you want, right, the divergence of the magnetic field is always zero, right? So then the dipole will be the dominant contribution, right? So, and the magnitude of the magnetic field in a dipole configuration decays as 1 over the distance cube. That's the main point. So you have a 1 over the distance cube decay, like shown here. Okay. And now the only thing that remains is fixing like these constants. Okay, so that is simple. Once you know the scaling of the decay of the magnetic field, the only thing you need to do is to fix the intensity of the field at a fiducial distance, and then you consider the distance, like you consider the distance with respect to the fiducial one. So the scaling of the distance of observation with respect to the fiducial distance where you know the magnitude of the field. Okay, so this is exactly what you do here. So in the paper that was referenced before, this Shahzadeh 2018 paper, it is studied that at around 4 r ISCO, so this is the innermost stable circular orbit radius, so at about 4 times this radius, the magnetic field roughly has an intensity of, well, it's 10 to the minus 2 Gauss per second times the scaling. Why Gauss per second? Because what the Birban battery mechanism does is that it gives you the rate of change of the magnetic field, but then you can scale it this way in order to get the intensity of the magnetic field. So this essentially computes the intensity of the magnetic field at this scale at 4 r ISCO, and then you just scale it with 1 over r cube away. Okay, so this is the point. Okay, now for the case of the magnetic primordial black holes, which are the primordial black holes which would have accreted the magnetic monopoles, right? Then essentially the magnitude of the magnetic field follows a Coulomb-like dilution, right? So the magnitude of the field will dilute itself as 1 over r squared, right? Same like with the Keplerian potential, right? So the force field of the Keplerian potential has the usual 1 over r squared dilution, right? So here it's the same, and like I mentioned, right, because of this fact that monopoles and anti-monopoles are accreted with equal probability, and therefore the net charge scales as square root of the number of total monopoles accreted. This basically gives you a scaling of square root of the mass of the black hole. Okay, and this is important. It will be important for the exercise later that this is a phenomenological Coulomb constant, if you want. It is like the magnetic analog phenomenological Coulomb constant. Okay, which has this weird form, but it basically relates the scaling of the mass of the primordial black hole with the actual magnetic charge. So this QM is the quantum of magnetic charge, which is given by the standard Dirac quantization conditions. So it is basically 1 over the charge of the electron with the correct dimension-full factors that you need to fix the dimensions, okay? But it has the scaling of square root of the magnetic monopole density in the universe divided by the primordial black hole density. So this is the mass density in primordial black hole. And the reason for this square root ratio is that you can imagine multiplying by the cosmic volume, by the cosmic Lagrangian volume occupied by the black hole. So let's say you had an overdense region in the early universe that collapsed into a black hole. This overdense region occupied a Lagrangian volume. So if you multiply both numerator and denominator inside the square root by this Lagrangian volume, it gives you capital N, which is the total number of magnetic monopoles that were present in the region that collapsed into the black hole, divided by M, by the total mass of the black hole, which is the mass of the black hole. And that one cancels with the square root of M in the expression for the magnetic field, and therefore it gives you capital N, right? So as it should, basically it will tell you that the force, the magnetic force, will be the square root of capital N times the magnetic charge of one monopole times mu 0 over 4 pi, which is like the Coulomb constant for the magnetic process, divided by r squared. Okay, so this is important. Okay, so now that we know the form of the magnetic field for each primordial black hole individually, now we need to know how to combine them in order to source the cosmic magnetic field. And the way to do this is to consider a power spectrum, okay? So here's the logic. We have the dark matter made of primordial black holes. The dark matter is distributed according to a matter power spectrum, which basically tells you the statistical properties of the distribution of overdensities of matter in the universe, in the early universe, or dark matter in the early universe. And therefore, it is reasonable to consider that the field fluctuation tracks the overdensity fluctuation of the matter. Okay, this will be made more clear later, but for now, we need to consider the form of the power spectrum. So this is the form of the matter power spectrum that we're considering. It is the standard lambda CDM power spectrum plus a Poisson tail. Okay, so the origin of this Poisson tail was briefly explained yesterday in the introduction by Nelson Padilla, and basically the point is that primordial black holes are huge dark matter particles, so finite size effects now are physical. So people that is more comfortable than myself with n-body cosmological simulations, they know that when you consider that your dark matter population in the simulation is made up of huge dark matter particles, you have all these finite size effects that essentially are Poisson noise that has to be filtered out. But in this case, the Poisson noise is real. It's because, you know, the dark matter particles are huge. They're not WIMPs, right? You know, particle physics candidates. They're actually objects that have a, you know, solar mass size, right? Like 10 to the 2 solar masses in the preferred model, actually. So this is your individual dark matter particles. So there are finite size effects that this time they're real. So you don't need to filter them out. You need to take them into account as a component of the power spectrum. So all the details of how this is done are in this very nice paper by Padilla et al. Of 2020. Okay, good. So now that we have the matter power spectrum, now we have to know how to combine everything in order to find the magnetic fluctuation. So here is the key equation of this workshop, okay? So this is the key equation. So what does it tell you? It tells you that the magnetic fluctuation can be written as the primordial black hole mass function, right, times the magnetic field of a single entity, so a single dark matter particle, times a certain softening function. So this softening function is essentially what softens out the potential, if you want to think about it. So because this field strength, let's call it field strength, this field strength of the magnetic field has a 1 over r to a certain power dependence. So of course it blows up when you have two magnetic particles that are infinitely close by, but this is unphysical because there will be a minimum expected separation between dark matter particles, each of which sources the magnetic field. So therefore you need this softening length, right? It's the standard thing that you consider also in simulation. Okay, and this function can be chosen in different ways, which will be touched upon later. And then all of that times the matter fluctuation field. So basically what this tells you is that we're positing that the magnetic fluctuation field tracks the matter fluctuation field, and the rest is just adding up. So basically you need to add up all the contributing entities per mass bin integrated in mass multiplied by the intensity of each entity times the softening of the separation between entities integrated over volume and integrated over mass. Okay, so this is a standard statistic construction. Okay, right, good. So now that we have this key formula and that it is well understood, Now I'm going to do a quick review of how you derive power spectra from density fluctuation or from entity fluctuation. So this is the power spectrum of an entity in terms of the entity fluctuation. In this case, it's magnetic power spectrum in terms of the magnetic fluctuation, right? So here are the ingredients that we reviewed. Just to mention, we're considering this particular softening function just for convenience, and it is taken from a Monte Carlo simulation. If you have more questions, you can ask later. This distance function, it is the average distance between primordial black holes of mass m. Okay, and it is essentially the number density of that mass scale to the power minus 1/3. Okay, this is like a global measure of the distance between primordial black holes of a certain mass scale. Okay, right. So with that defined, the main point is the following. This complicated function, you can write it in a very slick way. You can write it in terms of a certain window function times the matter fluctuation. And now you can use the same machinery that you use for matter power spectra. So take a look at this. All the spatial dependence in this formula, it is written in the way of a convolution, right? So essentially you have a convolution integration kernel that is being multiplied by this delta. And you just give a name to this convolution kernel. You call it F, let's say FB, right? And now the magnetic fluctuation, you can write it in terms of the convolution of this convolution kernel FB, which contains all the information about both the shape of the magnetic field and the cutoff function, etc., and the density fluctuation, okay? Right, so with that defined, now essentially you can consider the following. You can consider that, okay, first of all, you want to define the magnetic fluctuation in a certain scale, let's say in a ball of size capital R, and you do that using a usual window function. So in this case, because at the end of the day, I want to work in Fourier space, I'm just considering top hats in Fourier space, just as easy as that. And now you have the two fundamental theorems of power spectra computation, namely the convolution theorem and the Parseval theorem. With those two theorems, you can compute everything in power spectra. So basically, the point is the following. The Fourier transform of a convolution is the product of the Fourier transforms. That's the first one. And the second one, the Parseval theorem tells you that the real space average of the mod square of a function is equal to the Fourier space average of the mod square of the Fourier transform. That's the Parseval theorem. Okay, so with those two theorems, essentially you can do the standard thing, and if you have more questions, you can ask later, and you can find the scale for a spatial variance, right? The spatial variance, so this is the spatial magnetic variance written like this in terms of the Fourier transform of the window function, which is just a step in Fourier space, times the magnetic power spectrum, okay? Because the magnetic power spectrum, by definition, is the Fourier transform squared. So it is the square of the Fourier transform of the fluctuation of the field of this one, right? This is by definition, okay? And now the magnetic fluctuation essentially is given just by this product. Why? Because of the following. Because so here, the magnetic fluctuation was the convolution of the F and the delta. So therefore, by the convolution theorem, the Fourier transform of the magnetic fluctuation is just the product of the Fourier transform and the Fourier transform of the delta. So the Fourier transform of the F and the Fourier transform of the delta, okay? And knowing this, you just take the square of that, and here you have it. The square of the Fourier transform of the magnetic fluctuation will be equal to the square of the Fourier transform of the FB times the square of the Fourier transform of the delta, which is the matter power spectrum by definition. So finally, the result, one of the most important result here is that the magnetic power spectrum, you can write it just as the square of the Fourier transform of the window function FB, which contains all the information about the form of the magnetic field of a single black hole and also their spatial distribution. So namely, the mass function, all of that is contained in the FB, times the standard usual lambda CDM matter power spectrum. Okay, and now technical detail. Okay, so all that remains is to say how to compute this Fourier transform, namely the Fourier transform of FB. So if you remember, the FB, we define it in this way. Okay, so it can be written in this way, right? And now, basically, this G function is the one that contains the spatial dependence. So remember that 1 over R to the P is the form of the field strength, right? So in particular, P equals 2 in the case of the magnetic monopole, and P equals 3 in the case of the standard dynamo process, okay? And then this is the only part of the function that now has the spatial dependence. So because of linearity of the Fourier transform, taking the Fourier transform of the FB can be reduced into a mass integral of something that doesn't depend on the position times the Fourier transform of the G function. And the Fourier transform of the G function is a standard Fourier transform exercise in 3 dimensions. And here is the answer. This is the Fourier transform of the G. Okay, so now you have everything. And let me skip this. Just to summarize, this is what you obtain. So you obtain that the magnetic power spectrum is given by the square of the Fourier transform of the FB times the matter power spectrum, and the Fourier transform of the FB is given by this final form, okay? So this is already having computed the Fourier transform. Now it is just written in terms of an integral in R and in M that has to be done numerically, let's say, okay? Right, so with this out of the way, first, this means that now we have a way of obtaining a magnetic power spectrum given the following ingredients: a mass function, a matter power spectrum, and the shape for the magnetic field of a single primordial black hole. Okay, so now let's just take a quick look at this. Knowing the magnetic power spectrum, now we can find the square, like the average square, the square average of the magnetic field fluctuation, which is simply well, by Parseval theorem. So by definition, right, the square of the delta, right, it is this, okay, but by Parseval theorem, it is just the integral of the power spectrum. So the integral of the power spectrum gives you the variance, right? It gives you the variance of the field fluctuation, right? And that can be translated directly into the magnetic energy density, because the magnetic energy density is the average of the variance of the field, right? And that you can filter it at a certain scale. So for instance, if you want to look at the field strength, so the magnetic field strength at a certain scale, you need to just filter the power spectrum with the spatial scale that you want to isolate. Okay, that's all. Okay, so, and this is going to be important for the exercise. Okay, so now let me just jump ahead. Okay, so in particular, you can consider the following. So this is the general framework. Now, in the case of magnetic monopoles, an interesting exercise that you can do is to try to use the magnetic power spectrum in order to constrain the cosmic abundance of magnetic monopoles. Okay, so just to give the conceptual idea, how would you do that? You would do the following. You have the freedom of choosing this K, right? Because this is it's a fiducial, it's a phenomenological K, right? The effective Coulomb constant, if you want. Okay. So first, you compute the magnetic power spectrum for a fiducial value of the phenomenological Coulomb constant, and then you can fix the value of the fiducial Coulomb constant. So you can fix the value of this phenomenological K in order to match the expected intensity of the magnetic field. Right? So you can do that exercise. So let's say you want to match here, like, okay, so in our paper, we show that in order to recover like the large scale magnetic fields that you see today, that of the order to 10 to the minus 16, you need 10 to the minus 30 Gauss at redshift 20. So you use that as a pivot. So you can fix the phenomenological K in order to get these amplitudes of the magnetic field. And from that, you can infer the required number density of magnetic monopoles that would give you this phenomenological Coulomb constant K. Okay, and how do you do that? Well, here, let me just explain fast. Essentially, it all boils down to relating the K with this N mon. So the N mon is just the number density, so the cosmological number density of magnetic monopoles. So you can solve for N mon in terms of K and the other stuff, and you can write the primordial black hole density, the primordial black hole mass density, as this particular product of stuff. So this is the fraction of dark matter in primordial black holes. right? This is the fraction of dark matter with respect to the critical density, and this is the critical density at a certain redshift, okay? So let's say the redshift of formation of the primordial black holes, okay? And from that, and also knowing that the primordial black hole formation is well inside the radiation domination. So you can approximate the critical mass density just by rho rad over a to the 4, okay? And also the dark matter density scales at 1 over a cube. So knowing that, you can finally write that you can plug that back into the n-mon, and given a k, you can obtain this n-monopole, and then you can relate that to omega monopole today, which is the omega for magnetic monopole, which will be given simply by this. So the omega monopole will be the number density of monopoles today times the mass of each one of them divided by the critical density today. Right? And you can use that in order to get a value of magnetic monopole density of omega monopole required to match the magnetic field strength that you need in order to source present day magnetic fields at the cosmological scales. Okay, so let me stop here, and now we can move to the exercise. But if you want more details on this work, I encourage you to check a paper that I will mention later, the archive number. Okay, no, here it is, sorry. No, I don't have the reference. Okay, I will put it in the chat. Okay, thank you very much.
Okay. Thank you, Ignacio. I have here also the archive link of the paper.
I strongly advise you to use the Discord for these kind of things, because actually that will be kind of our archiving system in some way, because sometimes these the chats here they disappear, right? So
yes, you're right. Okay, can you see my screen?
Yes.
Great. Okay. So welcome to the hands-on session of this second day of the workshop. Thank you for the explanation, detailed explanation of all the integrals to calculate. So, okay, so the thing, let me share. Ignacio have put the link of the repository at the Discord platform, but I don't have I can share the link. Okay, so let's get. Idea is to all the script will run the main notebook of this exercise of this is in repository, so you can just enter the link and download the zip or use your favorite way to get this information. The unique thing is that you will need to put everything in one vector and then open this Python notebook as one start running. So the idea is that I will show you some ways to compute all the machinery needed for computing the magnetic strength in both the scenarios by Ignacio. So let me know, please, if you have already downloaded the. I can't see you because I'm sharing screen. So let me know if you're with the notebook already, or I have to wait a minute for that. So the notebook, the EPI notebook. Yes, this is a work in other people from Chile and Argentina. So this is the main reference that with our paper, which Ignacio mentioned, and it has all the details, the calculation and the results. So I invite you to have some questions for the explanation. Okay. I imagine you have the notebook open. Stop me and let me do any issues with that. So I think the technical part has been developed by Joaquin, presented his code in order to compute the functions in Press-Schecter formalism. So basically, I imagine that you could play it with code and you did proposed by Joaquin yesterday. The good want to just or import or use some of the packages that script Joaquin yesterday. I've already done that for you. So all the machinery you will need and the script are already in the repository. So you need to open the in the cells. So from fixing on formal time and HC scenarios presented by Joaquin yesterday. Model developed by Marcos and Martin, one of our collaborators, has been also added into the repository. This is the spatial integral that basically will be needed for the form of function P mentioned by Ignacio in his theoretical part. I will just use the package. We will also make use of this CPAC special function. In particular, we will use this integral, cosine integral. We will need to interpolate some data in the lambda column matter power spectrum and considering also possible noise, as Ignacio explained. So we will data that have been prepared for by Nelson. I will go into details later on. So we'll collect that data in order to compute the power spectrum. And for the integral, we will also make use of this package integral for. We'll just run this. Okay, just put some fundamental constants that will be used throughout the computation in this notebook. So the international system of units, and we want to use some astronomical system of units. In particular, we will use megaparsecs for length, solar masses for masses, second for time, and coulomb for charge. Here at the end is for all the fundamental. So the first step is to yesterday to initialize cosmology. So we to in code class and initialize it. Remember that the mass functions are fairly characterized by some parameters, in particular n parameters, n blue and s indices. So remember we are just already port this class from Joaquin code, so we can use it in order to just give a function and use it for the magnetic work. These parameters here, so the n star I will use is to the two polar masses, and each one of the cosmological scenarios Joaquin presented yesterday, I chose a blue index of 1.5 for the FCT and 3 for the HC. So these are within the constraint yesterday. The rest is to be equal to 20, and the corresponding scale factor will be using comoving. just initializing the cosmology, exactly the same as yesterday. But compute and plot the functions we already generated with this class. To that, we will fix some domains for the masses as well. We will use in log scale. So in particular, we will take masses around 10 to the minus 20 solar masses, and the final masses of around 3 or 4 masses. Okay, so basically we will take functions FCT and HC from Joaquin's code. We will vectorize them in order to plot them. I will here some functions. Basically, I will call it graph functions, just mass functions, both FCT and HC scenarios. The domain or the input here is the log of the mass to some to this, then we want to create this function. Here I'm trying the functions and plotting. So I will run the cell. We have the two the red one is a fixed formal time scenario, and this for the HC. So then let's compute these characteristic instance that will be used throughout later on for computing the magnetic field power spectrum. So remember that we have a measure of the distance between two equal mass primordial black holes. This is a non-local distance. It's a bit tricky, the definition, but at least it satisfies all the residual properties of this kind of distance must satisfy. So we want, of course, integrate up to infinity. We have already set up a range for our masses. And basically, it's a notation. It's final mass we already set up before. We need to compute, in this case, an integral of a function that depends on mass. So let me just mention this thing in a general way. So suppose that we want to integrate a function of the mass, but it's not exactly the function as taking the mass as a domain. We remember that Joaquin prepared things such that the input is the logarithm of the mass. This is pretty simple once you realize what you are doing and how to integrate out these quantities. Just a warning on the following. If you have a function, as Joaquin defined in his code, that takes as the input the logarithm of the mass, but you want to integrate with respect to the mass and not with respect to the logarithm, just remember to compute the determinant of the Jacobian of the transformation, in this case 1D, and you include, I think in your notebook is already included that here, so I'm just computing the determinant of. So we will need to include this one function. So first step, include this Jacobian in the function. So basically, I can the function, but now with the include to integrate afterwards. If I to for characteristic distance, so basically exactly here the characteristic distance I'm defining. So and see how they look as a function of mass. You can see that heavier or for massive black holes, we see that this distance goes to infinity, and this is quite reasonable because we expect that there's not a lot of massive primordial black holes. So in an average, we expect the distance between them to be large, and when the mass goes to the minor or the smallest values we consider, this distance basically tends to the average distance, which is basically the density of the primordial black holes to the -1/3, as Ignacio explained before. With this function, we will matter power. We took the data from the as well as the CMC Goldman code, CAM, and also took into account the contribution of the poisson, as Ignacio also explained. It's a paper by paper. You can also see that. The tables of this matter power spectra were already provided by Nelson. So basically, I'm reading here this need for complete that. So all files are, of course, in. So once we read the information for the Poisson, for the black contribution of CDM matter power spectrum, we interpolate this data that we will mean. So we will have log of frequency and log of contribution of the matter power spectrum. In particular, I choose the interpolation for the Poisson data and interpolation for the dark data that were pretty good. Here I'm just using the usual package interpolating provided by Python. What you have here is basically standard lambda CDM power spectrum, and here's some the contribution of the Poisson noise. So what we will do is, following Nelson's paper, just to add them, and that for the whole spectrum that was also shown by Ignacio. Ignacio showed with other examples, with other index, blue index, and other also n stars. I have already just chosen some of them in order to illustrate the code. Of course, things. And if you have the scripts with the data, you can also play. Okay. Primordial black hole machinery. We will move on. So let me give a brief review of what Ignacio have been explaining, in particular for the first magnetic field generation mechanism, that is the Birman battery. So Ignacio told us from battery basically predicts a quite dipolar magnetic field. We have chosen as a fiducial scale this 4 times the R ISCO. That is basically the innermost stable circular orbit of a rotating black hole. So basically, at 4 R ISCO, we can see that the magnetic field produced by this battery is about 10 to the minus 2 Gauss, 10 to the minus 2 Gauss, basically in these units. Then we scale this in coordinates. We compute the contribution field as was explained before. So basically, this is an index solution between this wind and the overdensity field. This window function is basically the product on the mass function provided by Joaquin times the magnetic fields of one unique primordial black hole in our population, weighted by this softening function and integrated out over the whole mass range. Like before, the power spectrum basically back the square of the Fourier transform of the function times the primordial lambda black matter E, basically the one in here. And now we will basically compute this Fourier transform using this integral and using Marcos package for computing the Fourier transform of this function G. The our function is a very well known result for potential black holes. So here defined as a function of m, in this case of log of m. Then I define m just to do and compute quantity. And put here m equals 1 because all the physics units are put here at the end, and that is the quotient between the angular momentum per mass and the mass of the hole. So we're considering that, if Ignacio mentioned that we're considering that this primordial black hole has their maximum speed, because what we want to compute is a bound for the maximum magnetic field that could be generated in this case with a beam mechanism. With ISCO, once we have the ISCO of magnetic field at 4 times our ISCO, so this is done here. Once we have this, we start computing the square of the Fourier transform function. So basically, I defined here as I am defining this here, and then use this quadrature. Then I vectorize. I just vectorizing them in order to compute functions I will show you before. I will plot. This takes a bit more time. So function we can compute here the magnetic power spectrum. We are just multiplying the seconds to the cube of the frequency. So this is basically how magnetic power spectrum of the Derive battery looks. As you can see, the scales are very, very small. And with magnetic power spectrum, we can compute the magnetic field. So what we compute is average square magnetic field, some length scale lambda, and redshift 20. Square root of to update and order, because what we want to measure is not an equal order limit of this magnetic field. So compute the integral and then square root. And what we get average value for provided with this Biermann mechanism, we are assuming we have a population holes such that each one of the elements of a population produce magnetic field with their own disk through Biermann. For both scenarios, for both F and H, with this of the M star, we see that the magnetic field in average is pretty small, even in the case of when the black hole is rotating faster. So basically, the results are, yeah, really disappointing, because the Biermann battery seems not to work, at least to produce the power magnetic field needed at this scale for to explain current rate of magnetic field. So some comments on this, I hope are also running every cell with me. So if there is some problem with so as I told you before, we assume that every PBH have an accretion disk capable to compute with the whole field, right? For I mean mechanism. Nevertheless, we see that from that come from calculations. Not common that PBA and primordial black holes of masses lower than could and risk. This is maybe some we have in the model. We have assumed a maximal PBH spin, I told you before, and the results are basically very small. Okay, so I present here an example of this mechanism that I explained before in the lecture. So the magnetic field, assuming the existence of monopoles of magnetic monopoles as an activity, right? So this start the random session, which you can basically, of course, in order to run the upcoming cells, you will need to run the cells before because you will need information about the lambda CDA as well, the mass function and the characteristic distance we called before. This machine is exactly the same. So the unique thing that changes here is the form of the magnetic field produced by each entity of our population of primordial black holes. The same as by Ignacio some minutes ago. So the first idea, the first part of the activity is very presenting the technical details as we discussed today. So the first thing is we can meet, we can get resistance 30 Gauss magnetic field to explain our current 10 to the minus 16 Gauss magnetic field strength as in the observation. So we have all the machinery. I have outlined exactly the analog of the Biermann battery, but now for the monopoles setup, you see that here this now using this Maldacena names because when Maldacena in a single paper proposed magnetic black holes, so I will just use okay, so working yourself. So basically, the idea is all average scenario using exactly the same functions. All functions are already defined. You have to run these cells. The key point here is that we will, as a first setup, it's just in order to compute the field, to assume that this K constant is. Of course, we will obtain magnetic field has sense because this one is much more less than one, but then we will scale this value of K such a way average magnetic field obtaining by this mechanism is further on 1. It's approximately 10 to the minus 30, C equal to 20. So we will get new value for the constant K that we print here. The idea is once you estimate this constant K, you can get back to the code, just plug this here in the cell, and again to verify you are obtaining with our mechanism the required order of the magnetic field at this epoch. So the first part of the second part of the activity is basically this variability and this value of this whether or not the estimation is okay sense or not. To that is basically to calculate the monopole abundance today. This value of K. So, for example, if we obtain a large value of monopole abundance today. In particular, we will be doing as an omega, we will compute omega. The result has sense. By itself, just compute the monopole abundance. Here are exactly the same definition provided by Ignacio before. A comment in this you need the value of estimated before. So please don't run this to put a number if you can get the value because of some problem. You can put whatever you want here, but it is to put the correct numbers. Then you will see which is the monopole. And to compute that, so that we will use the for the monopoles around 10 to the 16 electron volts. We have the conversion units at the very first cells. So the idea is to get, with these values of k, we compute before, is to get an estimate of this omega monopole and pass it, compare with some other omegas, like for omega matter, omega dark matter, omega, and see if it has sense or not. I won't give you the answers, read the paper as well, but I would like you to compute them and then discuss. Okay, so it's time to you work with that. So I will be working now. Let me know if you run all the cells before.
I am not trying, but I'm trying to follow you. So.
You follow that?
Yeah, I mean, I'm having problems to listen to you, but I hope the recording will be better. I mean, sometimes it's kind of blurry.
But it is because of your connection or my connection? I'm not having any other problem.
I think it's the internet connection, but still, I'm hoping that Google is smart enough that actually will record your voice instead of transmitting to me.
Okay. Hopefully. Okay.
But still, I'm
Confirm
following
that.
you. I don't know the rest.
Okay. What about the rest? Could follow the explanation, both this and on screen?
Hi, Marcelo. Joaquin here.
Hi, William. Yeah.
I was trying to, also following your explanation, maybe with some issues, trying to listen to you because of the connection, but hopefully things will look better in the recording. And I only encounter a problem because I also am running the notebook that you sent. And maybe just to tell people that there are some modules that you require for this particular a notebook to run. For example, MP Math, I think I have not put it as a module that was a requirement in the first session. So
The repository. No.
Yes, maybe just indicate if there's any issue like executing the notebook. Just people can do a pip install the missing module and things will work properly. So just to say that.
Okay. Thank you, Joaquin. Okay, we will do some minutes for the exercise, and then I will solve it with you.
Hi, Marcelo. So, yeah,
Yes.
I think it was pretty clear. I mean, yeah. So there were some issues with the audio, with the voice, but the exercise was pretty clear. It's just like an estimation of omega monopole, given that you can fix k, right? I mean, it's just that. So you gave the So you gave like all the functions that are needed, like power spectrum, mass function, and all of that, even the Fourier transform of G and all of that. You just put the ingredients together, and this will allow you to generate a graph of the magnetic power spectrum, and then you just play around with that graph in order to match the desired level of the intensity of the magnetic field, which is 10 to the minus 30 Gauss at 20, right? Yeah, exactly.
At 20, exactly.
Right.
Yes.
So you try to match that, and when you match that, you just read out the value of k that you used in order to accomplish that, and from that you can solve for omega monopole. That's essentially it, right?
Yes. Thank you.
Right. So one point though, that just to understand better, like to be clear, because right. So you generate the power spectrum, right? But yeah, of course, the power spectrum is like the square of the fluctuation, right, in k space. So, but you need to integrate it in k in order to get the amplitude, right? So basically,
yes,
you need to like either. So if you want to consider like the average amplitude in the whole, like in all the spatial scales, like the true average amplitude, right? So the average root mean square amplitude, you have to integrate the power spectrum over the entire k space, right? But when we made this comparison, we were looking at a certain scale, right? I think it was was it like one parsec? I think it was like something like that.
1 kiloparsec. Yes.
1 kiloparsec. Yeah, sorry. Yeah, because in comoving, yeah, of course, it's cosmological, right? So it's 1 comoving kiloparsec. This is the scale, right? Okay, right. So did you include the function of the Gauss? Yeah, there you have. Yeah. Okay, yeah. I just wanted to make sure if you had the Gaussian filter. If you included the Gaussian filter,
we have the Gaussian filter computation of the magnetic average and the integral before using this pre-basic.
Okay, perfect.
So rule integrate.
Great.
Yes.
So
we are taking that in now.
Great. Yeah. So then, yeah, the integral of the filtered power spectrum will directly give you the square of the amplitude of the magnetic field that you need. Exactly. Just like that. Right. Good. Right.
Exactly.
Okay, thank you.
We take the square root. We square root that, an approximation for all magnitude of the magnetic field.
Great. Perfect. Thank you.
So the idea also of this is that you can give us any other generation mechanism of the field of one black hole, and you can put it assuming the population of the black holes and see a fast estimation of magnetic rays population in range of interest. So I think that's also interesting because now you will have this view, so you can it just by changing the physics, the magnetic entity of the population. So that's can also change the scale here. We are also we just considering a scale and a particular resist, but if you want to resist, you can do it. The tools are mainly statistical. There is no theory sort of theory agnostic, if you want, model. This is as well for our proposal. So that okay, cool. you would finish at least the first part. Whole probably it's pretty trivial, but it's interesting to see how this. So I don't know if you have estimation already of this case values. Who dares to tell me?
Well, we couldn't hear you well, the last part, Marcelo.
Oh, sorry.
Oh.
Is better now?
I guess, I mean, more or less everything was quite clear. I don't know if you want to close with something else, because otherwise maybe we can continue by Discord. I think it could be useful as a backup plan.
Okay. If you want, can you hear me now?
Sorry?
Can you hear me now?
Yes.
Okay, so for time, probably I could solve part 1 and part 2 just in order to close the discussion and see what we obtain.
Mm-hmm.
Okay.
Perfect. Yeah, perfect.
Great. Okay, so first you could run list the cells. So I will constants to 1 for this case. I will compute just the magnetic power spectrum for this second monopole accretion mechanism. Okay, let's just plot this. We will use this no meaning because we're constant 1. With that, we compute now the average magnetic field obtained with its fictitious values of the constants. Look that the average magnetic field is big. It doesn't matter because we'll just adjust the value of k inside to obtain this order of magnitude for the magnetic field that redshift. So basically, set that is the value we want over the one we obtained before. So the values of k are of order or need to be of order -4 or to the magnetic field. So then we go back and plug this simply here and then compute all, just in order to, for curiosity, to see how the magnetic field power spectrum looks like. So look, okay, we have to the 7 now with the correct estimation. See the estimation of the constant k. We have, of course, small magnetic power spectrum, but we know that we are happy because at values of k can obtain a magnetic field of the order we. So the idea is to discuss about the meaning of this k, because of, if we take a parameter, a free parameter, do whatever we want, but the idea is to physical meaning. Monopole abundance using the formalism provided by Ignacio before. So basically, the monopole density scales as 1 over the scale factor to the cube. So we will compute this monopole density. I will factor for each scenario we got for k. So with that, we follow this is in this cell and just these definitions for computing the monopoles. The monopole, of course, is related with the constant K definition and the definition. This K is proportional to the square root of monopole density. Compute it now. So obtain a lot of monopoles to megaparsec cube. So you see this number and you say, okay, the K values we obtained have no sense probably, but if you compute the omega monopole this way, we see that actually this omega monopole turns out to be order 10 to the minus 16 and 10 to the minus 18. So when comparing this omega monopole with the omega monopole for cosmology at the very beginning, number for 10 to the minus 1, and the radiation 10 to the minus 5. The omega for the monopoles, the monopole abundance is ordered 10 to the minus 16 and minus 18 to the 3. So now and it helps us to try this possibility at this early epochs of magnetic monopoles. Don't worry about this large number. The omega has a correct scaling, fortunately. So I think I am done. So if you have any question or comment?
Just one question. So do you remember what was the like the observational limit for the omega monopole today? Like because the point is that this
yes, there was a work. There was a paper. I don't remember the author. It was 12, I think, maximum.
But it was within the observational limit, so it was tolerated. Like
it
looks like for sure, right? So just to like kind of like give a punchline. So it's like you know, it's an exotic magnetic field generating mechanism, but if you do the computation and you fix the K in order to reproduce the required magnetic field, the omega monopole that you find is in principle within observational constraints, even though the number density seems quite high. But it's because it's so early in the universe that actually translates into a present-day omega monopole that it is within observational limits. It's kind of like an important point that I just wanted to make.
Yes, thank you, Ignacio.
Thank you.
Showing the reference is by Medvedev and 2017, in which reports a maximum value of this omega monopole, of course defined as the way we are defining this in our work, we 10 to the 12, so we are within the constraints reported in these papers. Oh. Can you hear me?
Yeah, we can hear. Yeah.
That fortunate connection, I think.
Yeah, but it seems it was just in time because.
Okay, sorry. I don't know what's going on with it. I have meet every day, and I don't know why today is not working. So sorry for that.
It could be the storm. Okay, I will close the recording now.
Okay.